Is string theory right? Is it just fantasy? Caught in the landscape, out of touch with reality. Compactified on S5 or T-star S3. Space is a pure void. Why should it be stringy? 'Cause it's quantum, not classical, non-renormalizable. Anyway you quantize, you encounter infinity. You see. Quanta must interact via paths we understand, using Feynman diagrams. Often they will just rebound, but now and then they go another way. The quantum loop. Infinities will make you cry unless you can renormalize your model of baryons, fermions, and all other states of matter. Curved space, the graviton, can be thought of as a field, but these infinities are real. In a many-body loop diagram, our results diverge no matter what we do. A quantum soup. Kiss your fields goodbye. Guess Einstein's theory wasn't complete at all. I see extended 1D objects with no mass. What's their use? What's their use? Do they give us quark plasma? Can we minimize one function or describe this state?
Nambu Goto, how to quantize, I don't know.
I'm just a world sheet, please minimize me.
Here's just a world sheet from a string theory, re-parameterized by a Weil symmetry.
Fermi bows, open, closed, orientable.
Vibrations, oh, they become particles. Vibrations, they become particles. Vibrations, they become particles. Become particles. Become particles.
Oh, mamma mia, mamma mia.
Just say the particles. A tachyon, a dilaton, and gravity.
So we need 10 dimensions, and I'll tell you why.
Calculation.
So to get down to 4D, we compactify. Oh, Caleb. Manifold must be Caleb. If we want to preserve any of us about symmetry.
So much things I took one, 2A and 2B. Heterotic O and heterotic E. All I want through S and T duality. Thank you, Edwin, for that superstring revolution and your new M theory.
Всем привет, господа. Давненько, ну, хотя, если считать неделю, давненько не виделись. Не знаю, возможно, вы думали, что я уехал, но пока нет, на самом деле. Я отдыхал. Ну, если можно это считать отдыхом. Короче, что-то меня в теоретическую физику поперло, причем в квантовую физику. Вот. Ну, еще вчера я мог сказать, что последние 120 часов я потратил 70 часов на физику, то есть прямо вот 70 чистых часов. Остальные там 25 на сон и 25 на бытовуху. В общем, такие пироги. Нерд, альфа-бета-нерд, да, такие парадоксы бывают. Исписал хреново тучу вообще бумаг. Блин, это полные диаграммы Фейнмана, конечно, это отдельная. Но дело в том, что да, меня, в общем-то, общая теория относительности Эйнштейна с юности, глубокой юности не устраивала. Вот, там куча дыр. И да, ну вы только что видели в начале. Вчера нашел эту тему. Парень вообще красавчик. Кстати, ученый. Ну, наверное, этот стрим не будет, на самом деле, интересен большинству зрителей, но, возможно, 5%. Кстати, да, у меня 5 ученых в подписчиках, как минимум, по которых, по крайней мере, я знаю. Физик из Америки, наш физик, кибернетик из Турции, математик из Америки. Ну, в общем, так что будет, ну, как бы хейтик, это прикрытие, как обычно, да. Не думаю, что это будет... Я поэтому отключил все вообще. Не думаю, что будет какая-то сильная дискуссия. Врублю, наверное, лекции Фейнмана. А завтра, возможно, уеду уже. Вот. Так что решил постримить перед отъездом немного. Ну и да, отвлечься, а то и недолго тогда дурки с этими бесконечностями. Вообще полная супер гравитация, супер струны. Это надо вообще вырубить волюм. Аренку сейчас сыграем за Варлка. Ну и чисто вообще, конечно, буду лекцию Фейнмана слушать. Эти спины, эти реально кванты, все эти. Да уж. Что вряд ли это будет сильно интересно, но... Демон Wrath. Да, так что я включу, микрофон включу, если что-то, ну, между там 3 лекции, вроде часа 3, наверное, стрим проведу, может больше. Можно, конечно, если получится какая-то дискуссия, пообсуждать потом, после, особенно второй лекции. Первой, второй. Хотя что после первой, после второй, наверное. Если будут зрители, а если нет, то... Не факт же, что и комрады, профессоры, ученые сейчас сбегутся на онлайн. Так что... И да, когда такие промежутки. Ну-ка, посмотрим, сколько вообще людей-то сейчас есть. Ну да, не густо, совсем не густо. Ну и хорошо. Ладно, короче, я врублю лекцию Фейнмана, да и все. И буду собирать себе колодку и играть аренку. И все дела. Такс.
Ladies and gentlemen, it's my privilege to introduce the messenger lecturer, Professor Richard P. Feynman of the California Institute of Technology. Professor Feynman is a distinguished theoretical physicist, and he's done much to bring order out of the confusion which has marked much of the spectacular development in physics during the post-war period. Assistant professor here at Cornell City, one lesson matters. This
It's odd, but in the infrequent occasions when I've been called upon in a formal place to play the bongo drums, the introducer never seems to find it necessary to mention that I also do theoretical physics. I believe that's probably that we respect the arts more than the sciences. The artists of the Renaissance said that man's main concern should be for man. And yet, there are some other things of interest in the world. Even the artists appreciate sunsets and the ocean waves and the march of the stars across the heavens. And there is some reason then to talk of other things sometimes. As we look into these things, we get an aesthetic pleasure from them directly on observation. But there's also a rhythm and a pattern between the phenomena of nature, which isn't apparent to the eye, but only to the eye of analysis. And it's these rhythms and patterns which we call physical laws. What I want to talk about in this series of lectures is the general characteristics of these physical laws. That's even another level, if you will, of higher generality over the laws themselves. And it's really, all I am talking about is nature as seen as a result of detailed analysis. But only the most overall general qualities of nature is what I mainly wish to speak about. Now, such a topic has a tendency to become too philosophical because it becomes so general that a person talks in such generalities that everybody can understand him, and it's considered to be some deep philosophy. However, I would like to be rather more special, and I would like to be understood in an honest way rather than in a vague way to some extent. And so, if you don't mind, I'm going to try to give, instead of only the generalities, in this first lecture, an example of physical law, so that you have at least one example of the things about which I'm speaking generally. In this way, I can use this example again and again to give an instance to make a reality out of something which would otherwise be too abstract. Now, I've chosen for my special example of physical law to tell you about the theory of gravitation, or the phenomena of gravity. Why I chose gravity, I don't know. Whatever I chose, you would have asked the same question. Actually, it was one of the first great laws to be discovered, and it has an interesting history. You may say, yes, but then it's old hat. I would like to hear something about science, more modern science. More recent, perhaps, but not more modern. Modern science is exactly in the same tradition as the discoveries of the law of gravitation. It is only more recent discoveries that we would be talking about. And so I do not feel at all bad about telling you of the law of gravitation, because I am, in describing its history and the methods, the character of its discovery and its quality, talking about modern science, completely modern. This law has been called the greatest generalization achieved by the human mind. And you can get already from my introduction, I'm more interested not so much in the human mind as in the marvel of nature who can obey such an elegant and simple law as this law of gravitation. So our main concentration will not be on how clever we are to have found it all out, but on how clever she is to pay attention to it. Now, what is this law of gravitation that we're going to talk about? The law is that two bodies or bodies exert a force upon each other, which is inversely as the square of the distance between them and varies directly as the product of their masses. And mathematically, we can write that great law down in the formula, some kind of a constant times the product of the two masses divided by the square of the distance. Now, if I add the remark that a body reacts to a force by accelerating or by changing its velocity every second to an extent inversely as its mass. It reacts, it changes velocity more if the mass is lower and so on, inversely as the mass. Then I have said everything about the law of gravitation that needs to be said. Everything else is a consequence, a mathematical consequence of those two things that I said. That's a remarkable enough phenomenon in itself that the next lecture will consider this in more detail. Now, I know you're not all here. I know some of you are, but you're not all mathematicians, and so you cannot all immediately see all of the consequences of these two remarks. And so what I would like to do in this lecture is to briefly tell you the story of the discovery, tell you what some of the consequences are, what the effect of this discovery had on the history of science, what kinds of mysteries such a law entails, something about the refinements made by Einstein, and possibly the relation to other laws of physics. The history of the thing, briefly, is this, that the ancients first observed the way the planets seemed to move about in the sky and concluded that they all went around, along with the Earth, went around the sun. This discovery was later made independently by Copernicus after they had forgotten, that people had forgotten that it had already been made. Now, the next question that came up to study was exactly how do they go around the sun? That is, exactly what kind of motion? Do they go with the sun at the center of a circle, or do they go in some other kind of a curve? How fast do they move, and so on? And this discovery took longer to make. The times after Copernicus were times in which there were great debates about whether the planets in fact went around the sun along with the Earth, or whether the Earth was at the center of the universe, and so on. And there were considerable arguments about this. When a man named Tycho Brahe got an idea of a way of answering the question, he thought that it might perhaps be a good idea to look very, very carefully and to record where the planets actually appear in the sky, and then the alternative theories might be distinguished from one another. This is the key of modern science and is the beginning of the true understanding of nature, this idea that to look at the thing, to record the details, and to hope that in the information thus obtained may lie a clue to one or another of a possible theoretical interpretations. So Tycho, who was a rich man and owned, I believe, an island near Copenhagen, outfitted his island with great brass circles and special observing positions, situation chairs that you could look through little holes, and recorded night after night the position of the planets. It's only through such hard work that we can find out anything. When all these data were collected, they came into the hands of Kepler, who then tried to analyze what kinds of motions the planets made around the sun. And he did this by a method of trial and error. At one stage he thought he had it. He figured out that they went around the sun in circles with the sun off center, and noticed that one planet, I think it was Mars, but I don't know, was 8 minutes of arc off, and he decided that this was too big for Tycho Brahe to have made an error, and that this was not the right answer. So because of the precision of experiments, he was able to proceed and to go on to another trial, and found, in fact, ultimately this. 3 things. First, that the planets went in ellipses around the sun with the sun at the focus. An ellipse is a curve all artists know about because it's a foreshortened circle, or children know about because somebody told them that if you take a string and tie it to 2 tacks and put a pencil in there, it'll make an ellipse. These 2 tacks are the foci, and if the sun is here, the shape of the orbit of a planet around the sun is one of these curves. The next question is, and going around the ellipse, how does it go? Does it go faster when it's near the sun, slower when it's further from the sun, and so on? We take away the other focus, we have the sun then and the planet going around. And Kepler found the answer to this too. He found this. that if you put the position of the planet down at two times separated by some definite time, let's say 3 weeks, and then at another place in the orbit, put the positions of the planets again separated by 3 weeks, and draw lines from the sun to the planet, technically called radius vectors. But anyway, lines from the sun to the planet, then the area that's enclosed in the orbit of the planet and the two lines that are separated by the planet's position 3 weeks apart is the same no matter what part of the orbit the thing is on. So that it has to go faster when it's closer in order to get the same area as it goes slower when it's further away, and in this precise manner. Several years later, he found the third rule, and that had not to do with the exactly motion of a single planet around the sun, but related the various planets to each other. And it said that the times that it took the planet to go all the way around was related to the size of the orbit, and that the times went as the square root of the cube of the size of the orbit, and for the size of the orbit is the diameter all the way across the biggest distance on the ellipse. So he has these three laws, which are summarized by saying it's an ellipse, and that equal areas are swept in equal times, and that the time to go around varies as a 3/2 power of the size, the square root of the cube of the size. So there's three laws of Kepler, which is a very complete description of the motion of the planets around the sun. The next question was, what makes them go around? Well, how can we understand this in more detail? Or is there anything else to say? In the meantime, Galileo was investigating the laws of motion. Incidentally, at the time of Kepler, the problem of what drove the planets around the sun was answered by some people by saying that there were angels behind here beating their wings and pushing the planet along around orbit. As we'll see, that answer is not very far from the truth. The only difference is that the angels sit in a different direction and the wings go in a different direction. But the point that the angels sit in a different direction is the one that I must now come to. Galileo, in studying the laws of motion and doing a number of experiments to see how balls roll down inclined planes and pendulums swung and so on, discovered an idealization, a great principle called the principle of inertia, which is this: that if a thing has nothing acting on it, if an object has nothing acting on it and is going along at a certain velocity in a straight line, it will go at the same velocity at exactly the same straight line forever. Unbelievable though that may sound to anybody who has tried to make a ball roll forever, the idealization is correct, and that if there were no influences acting, such as the friction on the floor and so on, the thing would go at a uniform speed forever. The next point was made by Newton, who discussed the next question, which is when it doesn't go in a straight line, then what? And he answered this way, that a force is needed to change the velocity in any manner. First, for instance, if you're pushing it in a direction that it moves, it will speed up. If you find that it changes direction, then the force must have been sideways. And that the force can be measured by the product of two effects. First, how much does the velocity change in a small interval of time? How fast is the velocity changing? How much is it accelerating in this direction, or how much is the velocity changing when it changes direction? That's called the acceleration. And when that's multiplied by a coefficient called the mass of an object, or its inertia coefficient, then that together is a force. One can measure for instance, if one has a stone on the end of a string and swings it in a circle over his head, then one can measure, when one finds one has to pull, the reason is that the speed of the velocity, the speed is not changing as it goes around the circle, but it's changing its direction, so there must be perpetually an in-pulling force, and this is proportional to the mass, so that if we were to take two different objects, first swing one, and then swing another one at the same speed around the head and measure the force in the second one, that second one, the new force is bigger than the other force in the proportion that the masses are different. This is a way of measuring the masses, by how hard it is to change the speed. Now, then Newton saw from this that, for instance, to take a simple example, if a planet is going in a circle around the sun, no force is needed to make it go sideways tangentially. If there were no force at all on it, it would have just keep coasting this way. But actually, the planet doesn't keep coasting this way, but finds itself later not out here where it would go if there were no force at all, but further down toward the sun. In other words, its velocity, its motion, has been deflected toward the sun. So what the angels have to do is to beat their wings in toward the sun all the time, that the motion to keep it going in a straight line has no known reason. The reason why things coast forever has never been found out. The law of inertia is no known origin. So the angels don't exist, but the continuation of the motion does. But in order to obtain the falling operation, we do need a force. So it became apparent that the origin of that the force was toward the sun. As a matter of fact, Newton was able to demonstrate that the statement that equal areas are swept in equal times was a direct consequence of the simple idea that all of the changes in velocity are directed exactly to the sun, even in the elliptical case. And maybe I'll have time next time to show you how that works in detail. So from this law, he would confirm the idea that the force is toward the sun. And from knowing how the periods of the different planets vary with the distance away from the sun, it's possible to determine how that force must weaken at different distances, and he was able to determine that the force must vary inversely as the square of the distance. Now, so far, he hasn't said anything. Yes, because he only said two things which Kepler said in a different language. One is exactly equivalent to the statement that the force is toward the sun, and the other is exactly equivalent to the statement that the law is inversely as the square of the distance. But people had seen in telescopes the Jupiter's satellites going around Jupiter, and it looked like a little solar system, so the satellites were attracted to Jupiter. And the moon is attracted to the Earth, and this goes around the Earth, is attracted the same way. So it looks like everything's attracted to everything else. And so the next statement was to generalize this and to say that every object attracts every other object. If so, the Earth must be pulling on the moon, just as the sun pulls on the planet. But it's known that the Earth pulls on things because you're all sitting tightly in your seats in spite of your desires to float out of the hall at this time. The pull for objects on the Earth was well known in the phenomenon of gravitation. And it was Newton's idea then that maybe the gravitation which held the moon in the orbit also applied, was the same gravitation that pulled the objects toward the Earth. Now, it is easy to figure out how far the moon falls in 1 second. Because if it went in a straight line, you know the size of the orbit, you know it takes a month to go around, and if you figure out how far it goes in 1 second, you can figure out how far the circle of the moon's orbit has fallen below the straight line that it would have been in if it didn't go the way it does go. And this distance is 1/20th of an inch. Now, the moon is 60 times as far away from the Earth's center than we are. We're 4,000 miles away from the center, and the moon is 240,000 miles away from the center. So if the law of inverse square is right, an object at the Earth's surface should fall in 1 second by 1/20th of an inch times 3,600, being the square of 60, because the force has been weakened by 60 times 60 for the inverse square law in getting out there to the moon. And if you multiply a 20th of an inch by 3,600, you get about 16 feet. And lo, it is known already from Galileo's measurements that things fell in 1 second on the Earth's surface by 16 feet. So this meant, you see, that he was on the right track. There was no going back now. Because a new fact that was completely independent previously, which is the period of the moon's orbit and its distance from the Earth, was connected to another fact, which is how long it takes something to fall in 1 second. So this was a dramatic test that everything's all right. Further, he had a lot of other predictions. He was able to calculate what the shape of the orbit should be if the law were the inverse square, and found indeed that it was an ellipse. So he got 3 for 2, as it were. In addition, a number of new phenomena had their obvious explanations. One was the tides. The tides were due to the pull of the moon on the Earth. This had sometimes been thought of before, with the difficulty that if it's the pull of the moon on the Earth being here, the water's being pulled up to the moon, then there would only be one tide a day where that bump of water is under the moon. But actually, you know, there are tides every 12 hours roughly, and that's 2 tides a day. But there was also another school of thought that had a different conclusion. Their theory was that it was the Earth that was pulled by the moon away from the water. So actually, Newton was the first one to realize what actually was going on, that the force of the moon on the Earth and on the water is the same at the same distance, and that the water here is closer to the moon and the water here is further from the moon than the Earth, than the rigid Earth, so that the water is pulled more toward the moon here, and here is less toward the moon than the Earth, so that it's a combination of those 2 pictures that makes a double tide. Actually, the Earth does the same trick as the moon. It goes around a circle, really. I mean, the force of the moon on the Earth is balanced, but by what? By the fact that just like the moon goes in a circle to balance the Earth's force, the Earth is also going in a circle. Actually, the center of the circle is somewhere inside the Earth. It's also going in a circle to balance the moon. So the 2 of them go around a common center here, and if you wish, this water is thrown off by centrifugal force more than the Earth is, and this water is attracted more than the average of the Earth. At any rate, the tides were then explained, and the fact that there were 2 a day. A lot of other things became quite clear. Why the Earth is round, because everything gets pulled in. And why it isn't round, because it's spinning so that the outside gets thrown out a little bit and it balances. And why the sun and moon are round, and so on. Now, as the science developed and measurements were made ever more accurately, the tests of Newton's law became much more stringent. And the first careful tests involved the moons of Jupiter. By careful observations of the way they went around over a long period of time, one could be very careful to check that everything was according to Newton. And turned out not to be the case. The moons of Jupiter appeared to be first get sometimes 8 minutes ahead of time and sometimes 8 minutes behind schedule, where schedule is the calculated values according to Newton's laws. It was noticed that they were ahead of schedule when they were close, when Jupiter was close to the Earth, and behind schedule when it was far away, a rather odd circumstance. And Mr. Römer, having confidence in the law of gravitation, came to an interesting conclusion, that it takes light some time to travel from the moons to the Earth, and that what we're looking at when we see the moons are not how they are now, but how they were the time ago that it took the light to get here. Now, when Jupiter's near us, it takes less time for the light to come, and when Jupiter's further, it takes longer time, so he had to correct the observations for the differences in time, and by the fact that they were this much too early or that much too late, was able to determine the velocity of light. This was the first demonstration that light was not an instantaneously propagating material. I bring this particular matter to your attention because it illustrates something. That when a law is right, it can be used to find another one. That by having confidence in this law, if something is the matter, it suggests perhaps some other phenomenon. And if we had not known the law of gravitation, we would have taken much longer to find the speed of light, because we would not have known what to expect of Jupiter's satellites. This process has developed into an avalanche of discoveries. Each new discovery permits the tools for much more discovery, and this is the beginning of that avalanche, which has gone on now for 400 years in a continuous process, and we're still avalanching along at high speed at this time.
Oh well, let's make a break here. Hello there, everyone. Всем привет, кто там на СК смотрит. Вообще, лучше начало тогда стрима гляньте. Я там по-русски объяснил сейчас. Ретровейверу своему товарищу из Германии объясню, что и как. So yeah, I was totally deep in physics, theoretical physics, and trying to... You know, the problem is I'm not sure about English terminology here. But yeah, so it was my vacation, week of vacation, totally spent it on physics. Last 120 hours I spent 70 of them on physics. 70. Only 25 on sleep and well, 25 on, you know, just usual things. Crazy nerd. Alpha beta nerd paradox. But yeah, something like that. I hope he will not have a swipe. So yeah, tomorrow I probably will... Короче, да, завтра, вероятно, я уеду. Наконец-то. Не буду нердить физикой, пытаясь вывести общую теорию всего. Ибо Эйнштейновское ОТО вообще несовершенно ни разу. Никогда меня не устраивало. Soulfire or just interesting. Nah. So I guess I explained it. So yeah, if you want, just go rest. See you later. I don't think I will be off for a week now, but for maybe 3 days. Just some, you know, I want to go off from a city to mountains and forest, just to rest. Just to rest from everything. Так что продолжаем лекции Фейнмана. Вообще, на самом деле, Фейнман, но уже привычка Фейнман говорить, ибо с тех пор, как я о нем знал, тогда, ну как, гуглы уже были, но часто его неверие везде у нас как-то говорили Фейнман, а в итоге на самом деле Фейнман. Так что продолжим.
Another problem came up. The planets shouldn't really go in ellipses because, according to Newton's laws, they're not attracted only by the sun, but also they pull on each other a little bit, only a little bit, but a little bit is something, and will alter the motion a little bit. So Jupiter, Saturn, and Uranus were big planets that were known, and the calculations were made as to how slightly different than the perfect ellipses of Kepler the planets ought to be going, Jupiter, Saturn, and Uranus, by the pull of one on each other. And when they were finished, the calculations, I mean, and the observations, it was noticed that Jupiter and Saturn went according to the calculations, but that Uranus was doing something funny. Another opportunity for Newton's laws to be found wanting, but courage. Two men, both who made these calculations, Adams and Leverrier, independently and at almost exactly the same time, proposed that the motions of Uranus were due to an unseen as yet new planet. And they wrote letters to their respective observatories telling them to look. Turn your telescope and look there and you'll find a planet. How absurd, said one of the observatories, that some guy sitting with pieces of paper and pencils can tell us where we'd look to find something new planet. And the other observatory was more, less, the administration was different. And they found the Neptune. More recently, in the beginning of the 20th century, it became apparent that the motion of the planet Mercury was not exactly right. And this caused a lot of trouble and had no explanation until a modification of Newton's. This did show ultimately that Newton's laws were slightly off and that they had to be modified. I will not discuss the modification in detail. It was made by Einstein. Now the question is, how far does this law extend? Does it extend outside the solar system? And so I show on the first slide evidence that the law of gravitation is on a wider scale than just the solar system. Here is a series of 3 pictures of a so-called double star. There's a third star, fortunately, in the picture, so you can see that they're really turning around and that nobody just simply turned the frames of the pictures around, which is easy to do on astronomical pictures. But the stars are actually going around. And by watching these things and plotting the orbit, you see the orbit that they make on the next slide. It's evident that they're attracting each other and that they're going around in an ellipse. According to the way expected, these are a succession of pictures going for all these different periods of time. I think, yes, it goes around this way. They didn't see it well when it was too close, and here it is in 1905. My slide is very old. It's gone around maybe once more since. And you'll be happy except when you notice, if you have noticed already, that the center is not in a focus of the ellipse, but it's quite a bit off. So something's the matter with the law. No. God hasn't presented us with this orbit face on. It's tilted at a funny angle. And if you take an ellipse and mark its focus and then hold the paper at an odd angle and look at it in projection, the focus doesn't have to be at the focus of the projected image. So it's because its orbit is tilted in space that it looks that way. It looks like it's not the right pattern. But it's all right, and you can figure everything out satisfactorily for that. How about a bigger distance? There's forces between the stars. Does it go any further than these distances, which are not more than 2 or 3 times the solar system's diameter? Here's something in the next slide that's 100,000 times as big as the solar system in diameter. And this is a large number of stars, tremendous number of stars. This white spot is not a solid white spot. It's just because of the failure of our instruments to resolve it. But are very, very tiny dots, just like the other stars, well separated from one another, not hitting each other, each one falling through and back and forth through this great globular cluster. It's one of the most beautiful things in the sky, as good as sea waves. And the distribution of this material is perfectly clear that the thing that holds this together is the gravitational attraction of the stars for each other. And the distribution of the material in the sense of how the stars peter out as you go out in distance permits one to find out roughly what the law is of force between the stars, and of course it comes out right that it is roughly the inverse square. The accuracy of these calculations and measurements is not anywhere near as careful as in the solar system. Onward, as gravity extends. This is a little pinpoint inside of a big galaxy, and the next slide shows a typical galaxy. And it's clear that this thing again is held together somehow, and the only candidate that's reasonable is gravitation. But when we get to this size, we haven't any way any longer to check the inverse square law. But there seems to be no doubt that these great agglomerations of stars, and so these galaxies, which are 50 to 100,000 light years across, the solar system is, well, from the Earth to the Sun is only 8 light minutes. This is 100,000 light years that the gravity is extending even over these distances. And in the next slide is evidence that it extends even further. Here is what is called a cluster of galaxies. There's a galaxy here and here and here. There are galaxies here. They're all in one lump of galaxies, analogous to the cluster of stars, but this time what's clustered are those big babies that I showed you in this previous slide. Now this is as far as is about 1/10, or well, 100th maybe, of the size of the universe, and as far as we have any direct evidence that gravitational forces extend. So the Earth's gravitation, if we take the view, has no edge, as you may read in the newspapers when the planet gets outside the field of the gravitation. It keeps on going ever weaker and weaker, inversely as the square of the distance, dividing by 4 each time you're twice as far away, until it mingles with the strong fields and gets lost in the confusion of the strong fields of other stars, but altogether with the stars in its neighborhood pulls the other stars to form the galaxy, and altogether they pull on other galaxies to make a pattern, a cluster of galaxies. So the Earth's gravitational field never ends, but peters out very slowly in a precise and careful law, probably to the edges of the universe. The law of gravitation is different than many of the other, well, is very important in the economy or in the machinery of the universe. There are many places where gravity has its practical applications as far as the universe is concerned. But atypically, among all the other laws of physics, gravitation has relatively few practical applications. I mean, the new knowledge of the law, it has a lot of applications. It keeps people in their seats and so on. But it has few, the knowledge of the law has few practical applications, relatively speaking, compared to the other laws. This is one case in which I picked an atypical example. It is impossible, by the way, by picking one example of anything, to avoid picking one which is atypical in some sense. That's the wonder of the world. The only applications I could think of were first in some geophysical prospecting, in predicting the tides, nowadays, more modernly, in working out the motions of the satellites and planet probes and so on that we send up, and also modernly to calculate the predictions of the planet's position, which have great utility for astrologers to publish their predictions and horoscopes in the magazines. That's the strange world we live in, that all the advances in understanding are used only to continue the nonsense which has existed for 2,000 years. Now, that shows that gravitation extends to the great distances, but Newton said that everything attracted everything else. Do I attract you? Excuse me, do I attract you? I was going to say, excuse me, do I attract you physically? I didn't mean that. What I mean is it really true that two things attract each other? Can we make a direct test and not just wait for the planets and look at the planets to see if they attract each other? And this experiment, the direct test, was made by Cavendish on equipment which you see indicated on the next slide. If I got my slides right. Well, I made a mistake. I was talking about the importance of the gravitation. I was overwhelmed by my clever remark about astrologers and forgot to mention the important places where gravitation does have some real effect in the behavior of the universe. And one of the interesting ones is the formation of new stars. In this picture, which is a gaseous nebula inside our own galaxy, and there's not a lot of stars, but it's gas, there are places where the gas has been compressed or attracted to itself here. It starts perhaps by some kind of shock waves to get collected, but the remainder of the phenomenon is that gravitation pulls the cloud of gas closer and closer together. So big mobs of gas and dust collect and form balls, which as they fall still further, the heat generated by the falling lights them up and they become stars. And we have in the next slide some evidence of the creation of new stars. It is unfortunately harder to see than I thought it was when I looked at it before. But this is not exactly the same as this. This bump here is further out than here, and that this also has a new dot here. I have found better examples, but we're unable to produce a slide. There is one example of a star patch, a light that grew in a place within 200 days. So that when it was in the same kind of a condition of a gas cloud, when the gas collects too much together by gravitation, stars are born. And this is the beginning of new stars. So the stars belch out dirt and gases when they explode sometimes, and the dirt and gases then collect back again and make new stars. Sounds like perpetual motion. I now turn to the subject I meant to introduce, which was the experiments on the small scale to see whether things really attract each other. And I hope now that the next slide does indicate, this is the second try, Cavendish's experiment. The idea was to hang by a very, very fine quartz fiber a rod with two balls, and then put two large lead balls in the positions indicated here next to it on the side. Then, because of the attraction of the balls, there would be a slight twist of the fiber. It had to be done so delicately because the gravitational force between ordinary things is very, very tiny indeed, and there it was. And it was possible then to measure the force between these two balls. Cavendish called his experiment weighing the Earth. We're pedantic and careful today. We wouldn't let our students say that. We would have to say they're measuring the mass of the Earth. You know? But the reason he said that is the following. By a direct experiment, he was able to measure the force and the two masses and the distance, and thus determine the gravitational constant. You say, yes, but we have the same situation on the Earth. We know what the pull is, and we know what the mass of the object pulled is, and we know how far away we are, but we don't know either the mass of the Earth or the constant, but only the combination. So by measuring the constant and knowing the facts about the pull of the Earth, the mass of the Earth could be determined. So indirectly, this experiment was the first determination of how heavy or how massive is the ball on which we stand. It's a kind of an amazing achievement to find that out, and I think that's why Cavendish named his experiment that way instead of determining the constant in the gravitational equation, weighing the Earth. Oh. He incidentally was weighing the sun and everything else at the same time, because the pull of the sun is known in the same manner. Now, one other test of the law of gravitation is very interesting, and that is the question as to whether the pull is exactly proportional to the mass. If the pull is exactly proportional to the mass, and the reaction to forces, the motions induced by forces, the changes in velocity, are inversely proportional to the mass, that means that two objects of different mass will change their velocity in the same manner in a gravitational field. Or two different things, no matter what their mass, in a vacuum, will fall the same way toward the Earth. That's Galileo's old experiment from the Leaning Tower. I took my young son of 2.5 to the Leaning Tower of Pisa, and now every time a guest comes, he says, Leaning Tower. So, anyhow, it means, for example, that in a satellite, a man-made satellite, an object inside will go around the Earth in the same kind of an orbit as a satellite on the outside, and thus float in the middle, apparently. So that this fact that the force is exactly proportional to the mass and that the reactions are inversely proportional to the mass has this very interesting consequence. The question is, how accurate is it? And it has been measured by an experiment by a man named Voss in 1909, and very much more recently and more accurately by Dickey, and it is known that 1 part in 10,000 million, the mass is exactly proportional. The forces are exactly proportional to the mass. How it's possible to measure with that accuracy, I wish I had the time to explain, but I'm afraid I cannot. It's a remarkably clever. I'll give a hint, Howard. I'll give one hint there. Suppose that you wanted to measure whether it's true for the pull of the sun. You know, the sun is pulling us all. It pulls the Earth, too. But suppose you wanted to know whether you had a piece of lead here and a piece of copper here, or polyethylene and lead. It was first done with sandalwood. Now it's done with polyethylene. Whether the pull is exactly proportional to the inertia. The Earth is going around the sun, so these things are thrown out by inertia, and they're thrown out to the extent that these two objects have inertia. But they're attracted to the sun to the extent that they have mass in the attraction law. So if they're attracted to the sun in a different proportion than they're thrown out by inertia, one will be pulled toward the sun and the other away. And so hanging on another one of those Cavendish quartz fibers, the thing will twist toward the sun. It doesn't twist to this accuracy, so we know that the sun's attraction for these two objects is exactly proportional to their centrifugal effect, which is inertia. So the force of attraction on an object is exactly proportional to its coefficient of inertia. In other words, its mass. I should say something about the relation of gravitation to other forces, to other parts of nature, other phenomena in nature, and I'll have more to say of a general quality later. But there is one thing that's particularly interesting, and that is that the inverse square law appears again. It appears in the electrical laws, for instance, that electricity also exerts forces inversely as the square of the distance, this time between charges. And one thinks perhaps inverse square of the distance has some deep significance. Maybe gravity and electricity are different aspects of the same thing. No one has ever succeeded in making gravity and electricity different aspects of the same thing. Today, our theories of physics, the laws of physics, are a multitude of different parts and pieces that don't fit together very well. We don't understand the one exactly in terms of the other. We don't have one structure from which all is deduced. We have several pieces that don't quite fit exactly yet. And that's the reason why in these lectures, instead of having the ability to tell you what the law of physics is, I have to talk about the things that are common to the various laws, because we don't know, we don't understand the connection between them. But what's very strange is that there are certain things that are the same in both. But now let's look again at the law of electricity. The law goes inversely as the square of the distance. But the thing that is remarkable is the tremendous difference in the strength of the electrical and gravitational laws. People who want to make electricity and gravitation out of the same thing will find that electricity is so much more powerful than gravity that it's hard to believe they could both have the same origin. Now, how can I say one thing is more powerful than another? It depends upon how much charge you have and how much mass you have. I'm certainly, you can't talk about how strong gravity is by saying I take a lump of such and such a size, because you chose the size. If we try to get something that nature produces her own pure number that has nothing to do with inches or years or anything to do with our own dimensions, we can do it this way. If we take the fundamental particles, such as an electron, any different ones will give different numbers, but to get an idea of the number, take electrons. 2 electrons, a fundamental particle. It's an object. It's not something I don't have to tell you what units I measure in. It's 2 particles, the fundamental particles. And they repel each other inversely as the square of the distance due to electricity. And they attract each other inversely as the square of the distance due to gravitation. Question: what is the ratio of the gravitational force to the electrical force? And that is illustrated on the next slide. The ratio of the gravitational attraction to the electrical repulsion is given by a number with 42 digits. And goes off here. This is written very carefully out, so that's 42 digits. Now, therein lies a very deep mystery. Where could such a tremendous number come from? That means if you ever had a theory from which both of these things are to come, how could they come in such disproportion? From what equation has a solution which has, for one, 2 kinds of forces, an attraction and a repulsion, with that fantastic ratio? People have looked for such a large ratio in other places. They're looking for a large number. They hope, for example, that there's another large number. And if you want a large number, why not take the diameter of the universe to the diameter of a proton? Amazingly enough, it also is a number with 42 digits. And so an interesting proposal is made that this ratio is the same as the ratio of the size of the universe to the diameter of a proton. But the universe is expanding with time. And that would mean the gravitational constant is changing with time. And although that's a possibility, there's no evidence to indicate that it's in fact true, and there are several difficulties, partial indications that it doesn't, that the gravitational constant has not changed in that way. So this tremendous number remains a mystery. I must say, to finish about the theory of gravitation, 2 more things. One is that Einstein had to modify the laws of gravitation in accordance to with his principles of relativity. The first was, one of the principles was that effects cannot occur instantaneously, while Newton's theory said that the force was instantaneous. He has to modify Newton's laws. They have very small effects, these modifications. One of them is all masses fall. Light has energy, and energy is equivalent to mass, so light should fall. And it should mean that light going near the sun is deflected. It is. And also the force of gravitation is slightly modified in his theory, so that the laws slightly change, very, very slightly, and it is just the right amount to account for the slight discrepancy that was found in the movement of Mercury. Finally, with the connection to the laws of physics on a small scale, we have found that the behavior of matter on a small scale obeys laws so different, very different than things on a large scale. And so the question is, well, how does gravity look on a small scale? What is called the quantum theory of gravity? There is no quantum theory of gravity today. People have not succeeded completely in making a theory which is consistent with the uncertainty principles and the quantum mechanical principles. I'll discuss these principles in another lecture. Now, finally, you will say to me, yes, you told us what happens, but what is this gravity? Where does it come from, and what is it? Do you mean to tell me that the planet looks at the sun, sees how far it is, takes the inverse of the square of the distance, and then decides to move in accordance with that law and move? In other words, although I've stated a mathematical law, I haven't given you no clue as to the mechanism. I will discuss the possibility of doing this in the next lecture, which is the relation of mathematics to physics. But finally, in this lecture, I would like to remind, just at the end here, to emphasize some characteristics that the gravity has in common with the other laws that we have mentioned as we passed along. The first is that it's mathematical in its expression. The others are that way too. We'll discuss that next time. Second, it's not exact. Einstein had to modify it. We know it isn't quite right yet because they have to put the quantum theory in. That's the same with all our other laws. They're not exact. There's always an edge of mystery. There's always a place that we have some fiddling around to do yet. That, of course, is not a property, probably not a property. It may or may not be a property of nature, but it certainly is common with all the laws as we know them today. It may be only a lack of knowledge. But the most impressive fact is that gravity is simple. It is simple to state the principle completely and have not left any vagueness for anybody to change the ideas about. It's simple and therefore it's beautiful. It's simple in its pattern. I don't mean it's simple in its action. The motions of the various planets and the perturbations of one on another can be quite complicated to work out. Or to follow how all those stars in the globular cluster move is quite beyond our ability. It's complicated in its actions, but not in the basic pattern or the system underneath the whole thing, as that's a simple thing. That's common in all our laws. They all turn out to be simple things, although complex in their actual actions. Finally comes the universality of the gravitational law, the fact that it extends over. That Newton, in his mind worrying about the solar system, was able to predict what would happen in an experiment of Cavendish, where Cavendish's little model of the solar system, the two balls attracting, has to be expanded 10 million times to become the solar system. And then 10 million times expanded once again, and we find the galaxies attracting each other by exactly the same law. Nature uses only the longest threads to weave her patterns, so that each small piece of her fabric reveals the organization of the entire tapestry. Thank you.
Hello, Jake. Probably you didn't hear me till this time, right? Yeah, Jonas, I know about his new project. I just listened to some of the compositions. But we will discuss Feynman theories and overall his lection after second part. It will be another hour, because in this one, well, there are plenty of things, but just for global stuff, if we can say global. So yeah, I'll make a little break after this match. We'll turn on some funny stuff. Hey Jake, by the way, check out the beginning of the stream a little bit later, of course. Well, see for yourself. Just, I found a really great a cappella science guy. Oh yeah, so let me explain. Just tell there shortly to you. I was last week, it's kind of my holiday vacation from work, and what do you think? What was my rest? Damn it. It was physics. 70 hours, last 70 hours, totally deep in physics. Trying to... I'm not sure in English how it will be in English, like theory... Oh, damn, Dark Iron Skulker. The theory of all, not like, you know, Einstein's... but yeah, I'm just not sure about English terminology here. So I know, but I don't remember it actually. I remember Russian terminology. Wait. Damn. Don't even have better term in English? Oh. Okay, I see. So yeah, I mean, of course, theory of relativity by Einstein. I didn't like it from my deep youth, to say the truth. Not like, you know, didn't like, but I was not completely satisfied with it. You know, of course, you know about its holes. So yeah, I wrote huge quantity of stuff in the past week. It was my rest, kinda. Fucking alphabet nerd paradox. Yeah, I wasn't streaming a week. Probably people thought that I went somewhere, but no. Tomorrow maybe I will finally go for 3 or maybe more days. Yeah, about time cops. I don't remember how it's called. Let me check it. But yeah, it's kinda darker, not so, you know, not so light. Synth wave. It's more like a little bit dark and cosmic side. You can say division. Yeah, right. Kinda division. That Escape from Orion, which was introduced on TrueNeutralEvGenius channel, was a nice one as well. Okay, have a good time, have a good rest, Jonas. See you probably after some days, or maybe in near days anyway. So I was glad to see you as always. See you later. Shitty cards. Time for work, maybe. Not bad. Not bad. It's night. How to say night? Night working time, easily to say, for you, or what? Yeah, shift or session probably. Yeah, so session it's about like studying, right? It's not a term for a work. Or change maybe. Night change, night shift. So you are working hard on on a kinda on a factory term, I guess. Researching breaking RSA encryption in San Diego this summer. Quite interesting. We'll be here more often now. Okay. Jonas, see you. See you next time. Then for one. Assassin's Blade in Arena? Not bad, not bad. Damn it. I need to just destroy his face. I have Soulfire. Just one attack, 4 damage plus 4 damage, and that's it. But yeah, Feynman is such a such a troll. Great physicist, theoretical physicist, of course, and not only physicist as well. He was a musician, banging some drums. Quite an quite a developed guy. Huh. What the hell he is doing? Strange guy. Okay. Probably GG. And trolling. He had a good sense of humor as well. Yeah, GG. 5-0. Damn it. Bow before me. Stupid pesky humans before intellectual genius. Fucking plebs. So yeah, let's make a little break. I will turn on one funny stuff. It's not so serious as it was in the beginning about string theory and so on, but anyway, funny. It's one of my the most favorite musicals. It's Wicked. So yeah, when I found it, damn, I was like, holy fuck, these guys are really made great job. I'm not sure if you know it, but yeah, let me turn it on, and it will be, I don't know, 5-minute breaks. I will be a little bit AFK, so. And then let's continue. Feynman's lecture, part 2. There is a third part, but I'm not sure if I will write tomorrow. I need to go to sleep because yeah, I need to go up early. Well, we shall see. Maybe maybe the weather will be shitty and I will not go anywhere because it's kinda gale and storms are here for me, so yeah. I was under not snow but hail, probably, yeah, hail or torrent shower a couple of days ago. So not such a good weather for going somewhere, for traveling. Well, of course in mountains and forests it's not a big deal for me, but anyway. Mistaken his career comment. Yeah, every story of such how to say, not even science man, not even sciences, but just individuum, I guess I can say. It's always a huge story. It's always a very, very long story. I can take myself, for example, Feynman, Tesla, a lot of... Not actually, not a lot, but you know, there are a couple, not just single person in history, but yeah, there are a couple of great men with great life stories, and Feynman is one of them. Let me, yeah. So yeah, AFK for 5 minutes, something like that. Check this out. Wonderful, wonderful stuff.
Some new equations hit me. Something is not the same. I'm through with playing by the rules of Aristotle's game. Delay my spectrum testing. Delay the fluid notes I keep. It's time to trust my instincts and theorize. A leap. It's time to try defining gravity. I think I'll try defining gravity. To know why things fall down. I'm through inventing limits, the ones that Leibniz stole. Armed with this rate of change and 3 laws I already know. Too long I've been afraid of sharing my inverse square law. Well, here it comes, Principia Mathematica, in which I try defining gravity. Masses define the foci in gravity, and they're what pull things down.
Isaac, come with me. Think of what we could prove together. Limited. Your theory is so limited. Low energy limit of its geodesic twin, Newton. Space conveys attraction
With a Hilbert action, all semi-Riemannian. With space and time defining gravity. The end Einstein refining gravity. There's no such thing as down.
Well, are you coming?
I can't. I'm already dead.
Oh, right. Okay. I hope you're happy now that your proof exists.
You too. I hope it brings you bliss and you never wind up manic and deny quantum mechanics. I hope you're happy in the end. I hope you're happy, my
Someone you dare to join me, taking the quest to find one all-involving theory.
is ever gonna bring.
Okay, I'm back. Yeah, Bohemian Rhapsody. I started the stream with it. Yeah, it's really great. It's not even a parody, but huge work, and it's even explained where many great physicists and mathematicians, and me as well, where we stumbled fucking infinities and quantizing stuff. You know, this crazy infinities, quantizing, infinities, spins, fucking spins, Plancks, and you know, yeah, very quality, very great job. I'm just made a little break yesterday. You know, I could say yesterday that last 120 hours I spent like that, 70 hours on physics, 25 on sleep, and 25 on just usual things, you know. I know it's crazy, but yeah, it was my rest, kinda. Paradoxical alpha beta nerd. I'm repeating myself again. Just I already explained it to Jonas Retrowaver and in the beginning on Russian as well. But yeah. You're all fucking lazy bastards. So I need to repeat it, but never mind. What's up, by the way, Jake, about your mathematics stuff? And Defying Gravity is one of my favorite songs. Well, as I already said, Wicked is a very strong musical. I found it about, I don't know, 8 years ago, and I was quite impressed. While I was not a lover or liker of musicals, but yeah, this one, you know, this pop shit like Chicago and so on. Chicago, well, it's not that bad, but yeah, Wicked is another story. It's not a film, it's a theater one. But anyway, it's a great, very strong songs and music. Yeah, the first one for me was this one, String Theory. Kind of parody, if you can call it a parody, on a Queen's song, of course. Yeah, Bohemian Rhapsody. Okay, let's continue lecture second part, and then maybe we will have a discussion. But actually, what to discuss? Infinities, quantizing and stuff. Damn, just, and yeah, Feynman diagrams. Damn, crazy. Well, not crazy stuff, but you know the problems there, right? We have tons of papers now. Can rub my ass with them probably, because yeah, it's. But I will not surrender, of course. I will try again and again sometime, maybe later, after a year, after 2-3 years. You know, it's kinda like a thunder. Sometimes it's stuck in my head and I can spare a week or two for it, nearly get to a crazy house, or how to say, and then yeah, something like that. Oh, yeah. Madhouse, probably. Or lunatic asylum or something like that, yeah. Yeah, this is as well. By the way, I actually have five followers that are scientists, so you're not alone. I mean, without me. So, and I don't know about lurkers. Maybe there are some lurkers as well. So yeah, very glad about my audience. But of course, for majority it will not be interesting at all. I mean, such streams. But I don't give a fuck. Damn, this guy. So should I sulfire this shit? Probably yes. Sad. Damn. So, nah. Damn. No, I don't want to sulfire it. Okay, let's continue lecture. Second one.
Audience tonight. Hi. I can see the audience tonight, so I can see also from the size of it, which last time was a black spot in front of my eyes, that there must be many of you here who are not thoroughly familiar with physics. And also a number that are not too versed in mathematics, and I don't doubt that there are some who know neither physics nor mathematics very well. That puts a considerable challenge on a speaker who is going to speak on the relation of physics and mathematics, a challenge which I, however, will not accept. I published the title of the talk in clear and precise language and didn't make it sound like it was something it wasn't. It's the relation of physics and mathematics, and if you find that in some spots it assumes some minor knowledge of physics or mathematics, I cannot help it. It was named... In thinking of the applications of mathematics to physics, it's perfectly natural that mathematics will be useful when large numbers are involved in complex situations. Although, for example, if we took biology, the action of a virus on a bacterium is, if you watch it under the microscope, unmathematical. A jiggling virus finds some spot on this odd-shaped bacterium, and they're all different shapes, and finds some spot, and maybe it pushes its DNA in, and maybe it doesn't, and so forth. And yet, if we do the experiment with millions and billions of bacteria and viruses, then we can learn a great deal about the viruses by taking averages and working with large numbers. And we can use the mathematics involved in the averaging. We can see whether the viruses develop in the bacteria some new strains and in what percentage, and so we can study the genetics, the mutation, and so forth. To take another more trivial example, you know, imagine an enormous board, a checkerboard to play checkers, or drafts. And if the board is very large, the actual operation of any one step is not mathematical. It's very simple if it's mathematical at all. It either goes one side or the other on a diagonal, or it reaches and becomes a king and can go backwards when it reaches the end. In other words, the statement of the rules are very simple and do not really involve any mathematics. But you could imagine that on an enormous board with lots and lots of pieces, some analysis of the best move or good moves or bad moves might be made by a deep kind of reasoning which would involve somebody having gone off first and thought about it in great depth, and that becomes mathematics, this abstract reasoning. Another example is switching in computers. If you have one switch is either on or off, And there's nothing very mathematical about that, although mathematicians like to start there with their mathematics. But with all the interconnections and wires to figure out what a very large system will do, one requires a mathematics. And I would like immediately to say that a mathematics has its primary application, or it has a tremendous application in physics, in the discussion of the detailed phenomena in complicated situations, granting the fundamental rules of the game. And that is something which, if I were talking only about the relation of mathematics and physics, I would spend most of my time discussing. But since this is part of a series of lectures on the character of physical law, I do not have the time to discuss the applications of mathematics and physics to calculating what happens in complicated situations, but we'll go immediately to another question, which is the character of the fundamental law. If we go back to our checker game, the fundamental laws are the rules by which the checkers move. The mathematics may be applied in a complex situation to figure out what happens in the next move, what's a good move to make in a complicated situation, but very little mathematics is needed in the fundamental, simple character of the basic laws. Now, the strange thing about physics is that for the fundamental laws, we still need mathematics. For example, I give two examples, one in which we really do not and one in which we do. There's a law in physics called Faraday's law, which says that in an electrolysis, the amount of material which is deposited is proportional to the current and to the time that the current is acting. And that means that the amount of material is proportional to the charge which goes through the system. Sounds very mathematical. But what's actually happening is that electrons going through the wire each carry one charge. And to take an example, a particular example, it may be that to deposit one atom requires one electron to come. And so the number of atoms that are deposited is necessarily proportional to the number of electrons that flow, and thus to the charge that goes through the wire. So the mathematically appearing law has as its basis nothing very deep, requiring no real knowledge of mathematics, that one electron is needed for each atom in order for it to deposit itself. That's that's mathematics. I had to say number one. But it's not the kind of mathematics I'm talking about tonight. Now, if we take, on the other hand, Newton's law for gravitation, which has these aspects which I wrote down last time just to impress you with the speed at which mathematical symbols can carry information. We said that the force was proportional to the product of the masses of two objects, and inversely is the square of the distance between them, and that bodies react to forces by changing their speeds or changing their motions in the direction of the force by amounts proportional to the force and inversely proportional to their masses. Now that's words, all right, and I didn't have to write the equation, but nevertheless, it's kind of mathematical, and we would wonder, how can this be a fundamental law? How can this planet out there look, what does it do? It looks at the sun, and it sees how far away it is, and it decides to calculate on its internal adding machine the inverse of the square of the distance, and that tells it how much to move. This is certainly no explanation of the machinery of gravitation. So you might want to look further. And various people have tried to look further. Newton was originally asked, it doesn't mean anything, it doesn't tell us anything. He says, it tells you how it moves. It should be enough, I told you how it moves, not what. But people are often unsatisfied without a mechanism, and I would like to describe one theory which has been invented among others, of the type that you might want, that this is the result of large numbers. And that's why it's mathematical. And I give this theory, perhaps you've thought of it yourself. Every once in a while, some student comes running in, he suddenly explains gravitation. Suppose that in the world, everywhere, there are flying through us at very high speed a lot of particles that come equally in all directions. They're just shooting by, and once in a while hit us in a bombardment. But we and the sun are practically transparent for them, nearly. But some hit, and so it's not completely transparent. Then look what would happen. If the sun is here, and the earth is here, then if the sun weren't here, there would be particles bombarding from all sides, giving little impulses by the rattle of these bang, bang, the few that hit, which would not shake the earth in any particular direction, because there is many coming from one side as the other, from top, from bottom. However, when the sun is here, the particles which are coming in this direction are partly absorbed by the sun because some of them hit the sun and don't go through. Therefore, the number that are coming from this direction toward the earth is less. than the number that are coming from the other side, because here they have no opposition from no sun there. And it's easy to see, after some mental effort, that the further the sun is away, the less in proportion of all of the particles are being taken out of the possible directions in which particles can come. I mean, the solar size appears smaller. And, in fact, inversely is the square of the distance. So there will therefore be an impulse toward the sun on the Earth that's inversely as the square of the distance, and is the result of large numbers of very simple operations, just hit one after the other from all directions. And therefore the strangeness of the mathematical relation will be very much reduced, because the fundamental operation is much simpler than calculating the inverse of the square of the distance. This machine does the calculating, these particles bouncing. Only trouble with it is that it doesn't work for other reasons. Every theory that you make up has to be analyzed against all the possible consequences and to see if it predicts anything else. And this predicts something else. If the Earth is moving this way, more particles will hit it from the front than from the back. If you're running in the rain, more rain hits you in the front of the face than in the back of the head, because you're running into the rain. And so as the Earth is moving in this direction, it's running into the particles, rather, and running away from the ones that are chasing it from behind, so that more particles hit it from the front than from the back, and there would be a force also sideways whenever there was any motion. This sideways force would slow the Earth up in the orbit, and it certainly would not have lasted the at least 4 billion years that it has been going around the sun. So that's the end of that theory. Well, you say that was a good one, though. It got rid of the mathematics for a while. Maybe I can invent a better one. And maybe you can, because nobody knows the ultimate. But up to today, from the time of Newton, no one has invented another theoretical description of the mathematical machinery behind this law, which does anything else but say the same thing over again or make the mathematics harder, and at the same time doesn't produce some wrong phenomenon. I mean, they have, like this model does it, but it produces something which isn't true. So there is no model of the theory of gravitation today other than the mathematical form. If this were the only law of this character, it would be interesting and rather annoying. But what turns out to be true is that the more we investigate and the more laws we find and the deeper we penetrate nature, this disease, that every one of our laws is a purely mathematical statement in rather complex and abstruse mathematics. This is relatively simple mathematics. It gets more and more abstruse and more difficult as mathematics. And why? I haven't the slightest idea why. It is only my purpose in this lecture to tell you about this fact. In other words, it's my purpose in this lecture to explain, really, why I cannot satisfy you, if you do not understand mathematics too well, in trying to explain nature in any other way. It is the burden of this lecture, in fact, to just tell you the fact that it is impossible to answer honestly, the challenge of explaining in a way that a person can feel the beauties of the laws of nature without their having some deep understanding of mathematics. I'm sorry, but it seems to be the case. You might say, all right, then there's no explanation of the law. At least tell me what the law is. Why not tell me in words instead of in the symbols? Mathematics is just a language, and I ought to be able to translate the language. And in fact, I can. And with patience, I think I partly did. I could go a little further and explain more detail. That this means that if it's twice as far away, the force is 1/4 as much, and so on, and can convert all these into words. I would be, in other words, kind to the layman, as they all sit hopefully that you will explain something. And various different people get different reputations for their skill at explaining to the layman, in layman's language, these difficult and abstruse subjects. The layman then searches for book after book with the hope that he will avoid the complexity which ultimately set in even by the best expositor of this type. He reads the things hoping that one after he finds, as he reads, a generally increased confusion, one complicated statement after the other, one difficult to understand thing after the other, all apparently disconnected from one another, and it becomes a little obscure, and he hopes that maybe in some other book there's some explanation the man almost made it, you see. Maybe another fellow makes it right. And I don't think it's possible, because there's another feature. Mathematics is not just a language. Mathematics is a language plus reasoning. It's like a language plus logic. Mathematics is a tool for reasoning. It's in fact a big collection of the results of some person's careful thought and reasoning. By mathematics, it is possible to connect one statement to another. For instance, I can say that the force is directed toward the sun. I can also tell you, as I did before, that the planet moves so that if I draw a line from the sun to the planet and draw another one at some definite period, like 3 weeks later, the area that's swung out by the planet is exactly the same as it will be in the next 3 weeks and the next 3 weeks and so on as it goes around the sun. Now, I can explain both of those statements to you carefully, but I cannot explain why they're both the same. So that if you don't appreciate the mathematics, you cannot see that the great variety of facts, the enormous apparent complexity of nature with all its funny laws and rules, each of which have been carefully explained to you, are really very closely interwoven. That logic permits you to go from one up to the other. It may be unbelievable that I can demonstrate that equal times will be swept out if the forces are directed toward the sun. And just to, if I may try, I will show you one demonstration to show you that those two things really are equivalent. And so that you can appreciate that there's more to merely the statement of the two laws, that the two laws are connected such that reasoning alone will bring you from one to the other. And the mathematics is disorganized reasoning, and that it's good to know how to do that, so to appreciate the beauty of the relationship of the statement. So I'm going to prove, if I may, the relationship that if the forces are directed toward the sun, then the equal areas are swept out in equal time. So we start, here's the sun, and we imagine that at a certain time, let's say the planet is here, and is moving in such a way that, let's say 1 second later or 1 hour, pick any time, let's say 1 second later, it's moved in such a manner that it has gotten to the position 2. Now, if the sun did not exert any force on it, then by Galileo's principle, it would keep right on going in a straight line. So in the same interval of time, later, the next second, it'll move exactly the same distance in the same straight line to the position 3, were there no force. All right, now first we're going to show that if there's no force, equal areas are swept out in equal time. I remind you that the area of a triangle is half the base times the altitude, and that the altitude is the vertical distance to the base. And that if the triangle is sort of cockeyed, there's a name for it which I forget, obtuse, then the altitude is this vertical height here. See, I know about the triangles, I just don't know the name. Now let us draw the lines to these 2 points in the case that there was no motion whatsoever. The question, this doesn't draw very well, I'm not accurate, but these 2 distances are equal, remember. The question is, are these 2 areas equal? Well, consider the triangle made from the sun and the 2 points 1 and 2. It's this one. What's its area? It's this space multiplied by this height. And what about the other triangle, which is the triangle in motion from 2 to 3? It's this base times the same altitude. The 2 triangles have the same altitude and, as I indicated, the same base and have the same area. So far, so good. If there were no force from the sun, equal areas would be swept out in equal times. The 2 triangles have equal area. But there is a force from the sun. And during this interval, from 1 to 2 to 3, the sun is pulling and changing the motion in various directions, this way, that way. To get a good approximation to that, we'll take the central position or average position here and say that the whole effect during this interval was to change the motion by some amount in this direction toward the sun. That means that although the particles were moving this way and would have moved this way in the next second, because of the influence of the sun, the motion is altered by an amount that's poking in this direction. That's parallel to this, exactly parallel. These lines are parallel. It's the direction in which this new motion is. The new motion is a compound of what it wanted to do and the change that's been induced by the action of the sun. So it doesn't really end up at position 3, but rather at position 4. So now we would like to compare, it's getting complicated in the diagram, the triangle 2,4S and 2,3S. I'll show you that those are equal. Because they have the same base, those 2 triangles, this one here, and the one that happened when we had no force. The one with force and with no force have the same base. And do they have the same altitude? Sure, because they're included between parallel lines, and so they have the same altitude. And thus the area of the last triangle I drew is the same as the second one I drew, this 1, 2, 3, and that I had proved earlier was the same as the first one. So in the actual orbital motion of the planet, the area of the first, in second, and in the second are equal. So by reasoning, we can see a connection between the force, the fact that the force is toward the sun, and that the areas are equal. Not ingenious, no? This was, I borrowed this from Newton. It comes right out of the Principia, diagram and all. The letters are different, that's all, because he wrote in Latin. These are Arabic numerals. But incidentally, Newton made his proof geometrical like this, and made all his proofs in his book geometrical of this type. Today we don't use that kind of reasoning. We use a kind of analytic reasoning with symbols, which this kind of reasoning requires an ingenuity to draw the right triangles, the correct triangles, I mean, to notice about the areas and to figure out how to do it. You have to be clever. But there have been improvements in the methods of analysis so that one can be quite more stupid. And I write much faster, you're much more efficient then. And I want only to show what it looks like in the notation of the more modern mathematics, where you don't do anything but write a lot of symbols to figure it out. First, we would like to talk about how fast the area changes, and we represent that by area dot. And the area changes because of when the radius is swinging, it's the component of velocity at right angles to the radius times the radius that tells how fast the area changes. So this is the component of the radial distance multiplied by the velocity or rate of change of the distance. Now the question is whether the rate of change of area itself changes. The principle is it's not supposed to change. The rate of change of area is not supposed to change. So we differentiate, so-called, this again, and we put, that'll mean some little trick about putting dots in the right place. And that's all. You have to learn the tricks. It's just a series of rules that people have found out that are very powerful for such a thing. And this says the component of the velocity at right angles to the velocity. It is none. There is none. The velocity is in the same direction as itself. And the acceleration, which is this thing, the second derivative, or the derivative of velocity, is the force divided by the mass. So this says that the rate of change of the area is the component of force at right angles to the radius. But if the force is in the direction of the radius, as Newton said, then there's no force at right angles to the radius, and that means that the rate of change of area doesn't change. I just wanted to illustrate the different kinds of notation. Now, Newton knew how to do this, more or less, with slight different notations, but he wrote everything this way because he tried to make it possible for people to read his papers. He invented the calculus, which is this kind of mathematics, and is a good illustration of the relation of mathematics to physics. When the problems in physics get difficult, we may often look to the mathematicians who have already studied such a thing and have reasoned about such an item before and have prepared a line of reasoning for us to follow. On the other hand, they may not have, in which case we have to invent our own line of reasoning, which will then pass back to the mathematicians, because everybody who reasons carefully about anything is making a contribution to the knowledge of what happens when you think about something. And if you abstract it away and send it to the Department of Mathematics, they put it in the books as a branch of mathematics. Mathematics, then, is a way of going from one set of statements to another. It's evidently useful in physics because we have all these different ways that we can speak of things, and it permits us to develop consequences and analyze the situations and change the laws in different ways and to connect all the various statements, so that as a matter of fact, the total amount that a physicist knows is very little. He has only to remember the rules for getting from one place to another, and he's able to do it then. In other words, all of the various statements about equal times, the forces in a direction of the radius, and so on, are all interconnected by reasoning. Now an interesting question comes up. Is there some pattern to it? Is there a place to begin fundamental principles and deduce the whole works? Or is there some particular pattern or order in nature in which we can understand that these are more fundamental statements and these are more consequential statements? There are two kinds of ways of looking at mathematics, which for the purpose of this lecture I will call the Babylonian tradition and the Greek tradition. In Babylonian schools in mathematics, the student would learn something by doing a large number of examples until he caught on to the general rule. Also, a large amount of geometry, for example, was known. A lot of properties of circles, theorem of Pythagoras, for example, formulas for the areas of cubes and triangles and everything else. And some degree of argument was available to go from one thing to another. Tables of numerical quantities were available so that you could solve elaborate equations and so on. Everything was prepared for calculating things out. But Euclid discovered that there was a way in which all of the theorems of geometry could be ordered from a set of axioms that were particularly simple. And you're all familiar with that much geometry, I'm sure. But the Babylonian attitude was, if I make my way of talking, what I call Babylonian mathematics, is that you know all these various theorems and many of the connections in between, but you've never really realized that it could all come up from a bunch of axioms. Modern mathematics, the most modern mathematics, concentrates on axioms and demonstrations within a very definite framework of conventions of what's acceptable and not acceptable as axioms. For example, in geometry, they take something like Euclid's axioms, modified to be made more perfect, and then to show the deduction of the system. For instance, it would not be expected that a theorem like Pythagoras' that the sum of the squares of the areas of squares put on the sides of the triangle will equal the area of a square on a hypotenuse should be an axiom. On the other hand, from another point of view of geometry, that of Descartes, the Pythagorean theorem is an axiom. So the first thing we have to worry about is that even in mathematics, you can start in different places. Because of all these various theorems are interconnected by reasoning, there isn't any real way to say, well, these on the bottom here are the bottom, and these are connected through logic. Because if you were told this one instead, or this one, you could also run the logic the other way if you weren't told that one, and work out that one. It's like a bridge with lots of members, and it's over-connected. If pieces have dropped out, you can reconnect it another way. The mathematical tradition of today is to start with some particular ones which are chosen by some kind of convention to be axioms, and then to build up the structure from there. The Babylonian thing that I'm talking about, which I don't really not Babylonian, but is to say, well, I happen to know this, and I happen to know that, and maybe I know that, and I work everything out from there. And tomorrow I forgot that this was true, but I remembered that this was true, and then I reconstruct it again, and so on. I'm never quite sure of where I'm supposed to begin and where I'm supposed to end. I just remember enough all the time so that as the memory fades and the pieces fall out, I put the thing back together again every day. The method of starting from the axioms is not efficient in obtaining the theorems. In working something out in geometry, you're not very efficient if each time you have to start back at the axioms. But if you have to remember a few things in the geometry, you can always get somewhere else. It's much more efficient to do it the other way. And what the best axioms are not exactly the same, in fact are not ever the same, as the most efficient way of getting around in the territory. In physics, we need the Babylonian method and not the Euclidean or Greek method, and I would like to say why. The problem in the Euclidean method is to make something about the axioms a little bit more interesting or important. But the question that we have is, in the case of gravitation, is it more important, is it more basic, is it more fundamental, is it a better axiom to say that the force is directed toward the sun, or to say that equal areas are swept in equal time? Well, from one point of view, the forces is better, because if I state what the forces are, I can deal with a system with many particles in which the orbits are no longer ellipses because of the pull of one on the other, and the theorem about equal areas fails. Therefore, I think that the force law ought to be an axiom instead of the other. On the other hand, the principle that equal times are swept out in equal areas are swept out in equal times can be generalized when there's a system of a large number of particles to another theorem, which I had prepared to explain, but I see I'm running out of time. But there's another statement which is a little more general than equal areas in equal time. Well, I have to state what it is. It's rather complicated to say, and it's not quite as pretty as this one, but it's obviously the son of this one. I mean, it's the offspring. If you look at all these particles, Jupiter, Saturn, the sun, and all these things going around, lots of stars or whatever they are, all interacting with each other, and look at it from far away and project it on a plane, like this picture, then everything is moving this way, and moving that way, and so on. Then take any point at all say, this point, and then calculate how much each one is changing its area, how much area is being swept out by the radius to every particle, and add them all together. But wait, those masses which are heavier count more strongly. If this is twice as heavy as this one, then this area it counts twice as much. So, order now, gravity generalization. The total of all of that is not changing in time. That's the generalization, obviously, of the other one. Incidentally, the total of that is called the angular momentum. And this is called the law of conservation of angular momentum. Conservation just means that it doesn't change. Now, one of the consequences of this is, just to show what it's good for, imagine a lot of stars falling together to form a nebula, a galaxy. As they come closer in, if they were very far out and moving slowly, so there was a little bit of area being generated, but on very long arms, distances from the center, then if the thing falls in, the distances to the center are shorter now. If all the stars are now close in, then these radii are smaller. And in order to sweep out the same area, they have to go a lot faster. So as the things come in, they swirl around, and thus we can roughly understand the qualitative shape of the spiral nebulae. You can also understand in the same way, exactly the same way a skater spins when you start with their leg out, moving slowly, and as you pull the leg in, it spins faster because when the leg is out, it's contributing, when it's moving slowly, a certain amount of area per second, and then when it comes in to get the same area, you have to go around faster. But I didn't prove it for the skater. The skater uses muscle force. Gravity is a different force, yet it's true for the skater. Now we have a problem. We can deduce often from one part of physics, like the law of gravitation, a principle, which turns out to be much more valid than the derivation. This doesn't happen in mathematics, that the theorems come out in places where they're not supposed to be. In other words, if we were to say that the postulates of physics were the law of gravitation, we could deduce the conservation of angular momentum, but only for gravitation. But we discover experimentally that the conservation of angular momentum is a much wider thing. Now, Newton had other postulates by which he could get the more general conservation law of angular momentum, but Newtonian laws were wrong. There's no forces, it's all a lot of baloney, the particles don't have orbits, and so on. Yet, the analog, the exact transformation of this principle about the areas, the conservation of angular momentum, is true with atomic motions in quantum mechanics and is still, as far as we can tell today, exact. So we have these wide principles which sweep across all the different laws. And if one takes too seriously his derivations and feels that this is only valid because this is valid, you cannot understand the interconnections of the different branches of physics. Someday, when physics is complete, then maybe with this kind of argument, we know all the laws, then we could start with some axioms, and no doubt somebody will figure out a particular way of doing it. And then all the deduction will be made. But while we don't know all the laws, we can use some to make guesses at theorems which extend beyond the proof. So in order to understand the physics, one must always have a neat balance and contain in his head all of the various propositions and their interrelationships, because the laws often extend beyond the range of their deductions. This will only have no importance when all the laws are known. Another thing that's interesting in the relation of mathematics to physics is this. A very strange thing, that by mathematical arguments you can show that you can start from very many different apparent starting points and come to the same thing. That's pretty clear. If you have axioms, you can use some of the theorems. But actually, in the physical laws are so delicately constructed that the statements of them have such qualitatively different character that it's very interesting. So if you'll permit me, I'm going to state the law of gravitation in 3 different ways, all of which are exactly equivalent, it turns out. But they sound completely different. 1, there's the forces between the objects as described before, and each object, when it sees the force on it, accelerates or changes its motion, rather, at a certain amount per second, as I've described before. The regular way, I call it Newton's law. Now there's a completely different way. That law says that the force depends on something at a finite distance away. See, it has what we call a non-local quality. The force on this depends on where that one is over there. Now, you may know the idea of action at a distance, but it can know what's going on over there. So then there's another way of stating the laws, which are very strange, and it's called the field way of representing the laws. And it's so very hard to explain, but I just want to give you some rough idea of what it's like. And it says, different thing, completely different thing, that there's a number at every point in space. I know it's a number. It's not a mechanism. It's the trouble with this whole physics, that it must be mathematical this way. There's a number at every point in space. Here's a number, and so on. And the number's changing. It changes, rather, when you go from place to place. If an object is placed at one of these points, at somewhere in space, the force on it is in the direction in which that number, I'll call it the name it's given, called a potential, is in a direction in which that potential changes as quick as it can. And the force is proportional to how fast it changes as you move. That's one statement. That's not enough yet, because I have to tell you now how to determine how the potential varies. I could say the potential varies as 1 over the distance from each object. But that's back to the action at a distance idea. However, the force is at a distance, but you can state the law in another way, and it says the following. You don't have to know what's going on anywhere outside of a little ball. If you want to know what the potential is here, you tell me what it is on the surface of any ball, no matter how small. You don't have to look outside. You just tell me what is in the neighborhood and how much mass there is in the ball. The rule is this, that the potential at the center is equal to the average of the potential on the little ball surface minus this constant that's over there in the other equation, divided by twice the radius of the ball. Let's suppose the radius of the ball is called A, and then multiplied by the mass that's inside the ball, if the ball is small enough. Now you see that this law is different than the other one because it only tells what happens at one point in terms of what happens very close by. Newton's laws tell what happened at one time in terms of what happens in another instant. It gives from instant to instant how to work it out. But in space, it leaps from place to place. But this thing is both local in time and also local in space, because it depends only on what's in the neighborhood. And there's another way of representing. That's another way. Now, there's a completely different way. See, there's a difference in the philosophy, in the qualitative ideas involved. You don't like action at a distance, you can get away without it. Now I'll show you one which is philosophically the exact opposite, in which there's no discussion at all about how the thing works its way from place to place, in which the whole thing is an overall statement, as goes as follows. When you have other particles around and you want to know how this one moves from one place to another, you do it as follows. You calculate a certain quantity you invent a possible motion that gets from one given place to some other place that you're interested in a given amount of time. Say it wants to go from here to here in an hour, and you want to know by what route it can get from there to there in an hour, by what curve. So what you do is you calculate a quantity guessing the curve. If you try this curve, you calculate a certain number for this quantity. I don't want to just say what the quantity is, but for those who have heard of these terms, this quantity on this route is the average of the difference between the kinetic and potential energy. Now, if you calculate this quantity for this route and for another route, you'll get, of course, different numbers for the answer. But there's one route which gives the least possible number for that, and that's the route that the particle takes. Now we're describing the actual motion, the ellipse, by saying something about the whole curve. We have lost the idea of causality, that the particle's here, it sees the pull, it moves to here, it pulls. Instead of that, in some grand fashion, it smells all the curves around here, all the possibilities, and decides which one to take. This is an example of the wide range of beautiful ways of describing nature, and that when people talk that nature must have causality, well, you could talk about it this way. Nature must be stated in terms of a minimum principle. Well, you can talk about it this way. Nature must have a local field. You can do that, and so on. And the question is, which one is right? Now, if these various alternatives are mathematically not exactly equivalent, And if for certain ones there will be different consequences than for others, then that's perfectly all right then, because we have only to do the experiments to find out which way nature actually chooses to do it. Mostly people come along and they argue philosophically, they like this one better than that one, but we have learned from much experience that all intuitions about what nature's going to do philosophically fail. It never works. One just has to work out all the possibilities and just try all the alternatives. Now, in this particular case that I'm talking about here, these theories are exactly equivalent. The mathematical consequences in every one of the different formulations of the three formulations, Newton's laws, the local field method, and this minimum principle, give exactly the same consequences. What do we do then? You will read in all the books that we therefore cannot decide scientifically on one or the other. That's true. They're not equivalent. They are equivalent. Scientifically, it is impossible to make a decision, because there's no experimental way to distinguish if all the consequences are the same. Psychologically, they're very different in two ways. First, philosophically, you like them or don't like them. Training is the only thing you can do to beat that disease. Second, psychologically, they're different because they're completely unequivalent when you go to guess at a new law. As long as a physics is incomplete and we're trying to find out the other laws and to understand the other laws, then the different possible formulations give clues as to what might happen in other circumstances. And they become not equivalent in psychologically suggesting to us the guess as to what the laws might look like in a wider situation. For instance, Einstein noticed that the law of gravity, he said that he realized that signals couldn't propagate faster than the speed of light, for electricity. He guessed that it was a general principle, the same guessing game as taking this angular momentum and extending it from one case where you proved it to the rest of the universe. He guessed that it was true of everything, and he guessed that it would be true of gravitation. If the signals can't go any faster than the speed of light, it turns out that the method of describing the forces instantaneously is very poor. And in the Einstein generalization of gravitation, this method of describing physics is hopelessly inadequate and enormously complicated, whereas this one is neat and simple, and so is this one. So we haven't decided between those two yet. In fact, it turns out that the quantum mechanics says that, and exactly as I stated them, neither is right, but that the fact that a minimum principle exists turns out to be a consequence of the fact that on a small scale, particles obey quantum mechanics. And the fact is the best laws at present understood is really a combination of the two, in which we use minimum principles plus local laws. And the present day believes that the laws of physics have to have the local character and also the minimum principle. But we don't really know. So it's this way, that if you have a structure that's only partly accurate and something is going to fail, if you write it with just the right axioms, maybe only one axiom fails and the rest remains. Just change one little thing. But if you write it with another set of axioms, they all collapse because they all lean on that. But we can't tell ahead of time, without some intuition and guesswork, as to which is the best way to write it until we find out the new situation. So we must therefore always keep all of the alternative ways of looking at the thing in our heads. So the physicists do Babylonian mathematics and pay little attention to the precise reasoning from fixed axioms. One of the amazing characteristics of nature is this variety of interpretational schemes which is possible. It turns out that it's only possible because the laws are just so and special and delicate. For instance, that the law is the inverse square is what permits it to become local. If it were the inverse cube, it couldn't be done this way. That the other end of the equation, that the force is related to the rate of change of the velocity, that's a consequence that permits this kind of a way of writing the laws, the minimum principle, because, for instance, if the force were proportional to the rate of change of position instead of velocity, you couldn't write it in that way. If you try to modify the laws much, you find you can only write them in a very much fewer ways. I always find that mysterious, and I don't understand the reason why it is that the laws of physics always seem to be possible to be expressed in such a tremendous variety of ways. They seem to be able to get through several wickets at the same time. Now I would like to make a number of remarks on the relation of mathematics and physics, which are a little more general. The first is that the mathematicians only are dealing with the structure of the reasoning, and they do not really care about what they're talking. They don't even need to know what they're talking about, or as they themselves say, or whether what they say is true. Now I explain that. If you state the axioms, you say such and such is so, and such and such is so, and such is so, what then? Then the logic can be carried out without knowing what the such and such words mean. That is, if the statements about the axioms are true, are carefully formulated and complete enough, it is not necessary for the man who's doing the reasoning to have any knowledge of the meaning of these words, and he'll be able to deduce in the same language new conclusions. If I use the word triangle in one of the axioms, there'd be some statement about triangles in the conclusion, whereas the man who's doing the reasoning might not know what the triangle is. But then I can read his thing back and say, oh, a triangle, that's just a three-sided what have you, that's a so-and-so. And so I know this new fact. In other words, mathematicians prepare abstract reasoning that's ready to be used if you will only have a set of axioms about the real world. But the physicist has meaning to all the phrases. And there's a very important thing that a lot of people who study physics that come from mathematics don't appreciate. The physics is not mathematics, and mathematics is not physics. One helps the other. But you have to have some understanding of the connection of the words with the real world. It's necessary to, at the end, to translate what you figured out into English, into the world, into the blocks of copper and glass that you're going to do the experiments with to find out whether the consequences are true. And this is a problem which is not a problem of mathematics at all. I've already mentioned one other relationship that, of course, it's obvious how the mathematical reasonings which have been developed are of great power and use for physicists. On the other hand, sometimes the physicist's reasoning is useful for mathematicians. Mathematicians also like to make their reasoning as general as possible. If you say, I have a three-dimensional space, or the ordinary space, I want to talk about ordinary space. You know, you're in it and you measure distances and there are three numbers you need to tell where something is. You go breadth, width, and height, three-dimensional space, and you begin to ask them about theorems. Then they say, now look, if you had a space of n dimensions, then here are the theorems. Well, I say, yeah, but I only want the case 3. Well, substitute n equals 3. And then it turns out that very many of the complicated theorems they have are much simpler because it happens to be a special case. Now, the physicist is always interested in the special case. He's never interested in the general case. He's talking about something. He's not talking abstractly about anything. He knows what he's talking about. He wants to discuss the gravity law. He doesn't want the arbitrary force case. He wants the gravity law. And so there's a certain amount of reducing, because the mathematicians have prepared these things for a wide range of problems, which is very useful. And later on, it always turns out that the poor physicist has to come back and says, excuse me, when you wanted to tell me about the 4 dimensions. Now, another item that's interesting in this relationship is the question of how to do new physics. Is it important to have a feeling, a kind of intuition? Oh, I must mention one other item. When you know what it is you're talking about, that these things are forces, and these are masses, and this is inertia, and this is so on, then you can use an awful lot of common sense, seat-of-the-pants feeling about the world. You've seen various things. You know more or less how the phenomenon is going to behave. Well, the poor mathematician, he translates it into equations, and the symbols don't mean anything to him, and he has no guide but precise mathematical rigor and care in the argument. Whereas a physicist who knows more or less how the answer is going to come out can sort of guess part way and go right along rather rapidly. The mathematical rigor of great precision is not very useful in the physics, nor is the modern attitude in mathematics to look at axioms. Now, mathematicians can do what they want to do. One should not criticize them because they are not slaves to physics. It is not necessary that just because this will be useful to you, they have to do it that way. They can do what they will. It's their own job. And if you want something else, then you work it out yourself. The next point is the question of whether we should guess, when we try to get a new law, whether we should use the seat-of-the-pants feeling and philosophical principles. I don't like a minimum principle, or I do like a minimum principle, or I don't like action at a distance, or I do like action. The question is, to what extent models help? And it's a very interesting thing. Very often models help, and most physics teachers try to teach how to use these models and get a good physical feel for how things are going to work out. But the greatest discoveries, it always turns out, abstract away from the model. It never did any good. Maxwell's discovery of electrodynamics was first made with a lot of imaginary wheels and idlers and everything else in space. If you got rid of all the idlers and everything else in space, the thing was okay. Dirac discovered the correct laws of quantum mechanics for relativity quantum mechanics simply by guessing the equation. And the method of guessing the equation seems to be a pretty effective way of guessing new laws. This shows, again, that mathematics is a deep way of expressing nature, and attempts to express nature in philosophical principles or in seat-of-the-pants mechanical feelings is not an efficient way. I must say that there is possible, and I've often made the hypothesis, that physics ultimately will not require a mathematical statement, that the machinery ultimately will be revealed, just a prejudice like one of these other prejudices. It always bothers me that in spite of all this local business, what goes on in a tiny, no matter how tiny a region of space, and no matter how tiny a region of time, according to the laws as we understand them today, takes a computing machine an infinite number of logical operations to figure out. Now, how can all that be going on in that tiny space? Why should it take an infinite amount of logic to figure out what one stinky tiny bit of space-time is going to do? And so I made a hypothesis often that the laws are going to turn out to be, in the end, simple like the checkerboard, and that all the complexity is from size. But that is of the same nature as the other speculations that other people make. It says, I like it, you don't like it. It's not good to be too prejudiced about the thing. To summarize, I would use the words of Jeans, who said that the great architect seems to be a mathematician. And for you who don't know mathematics, it's really quite difficult to get a real feeling across up to the beauty, or the deepest beauty of nature. C.P. Snow talked about two cultures. I really think that those two cultures are people who do and people who do not have had this, people who have had and people who have not had this experience of understanding mathematics well enough to appreciate nature once. It's too bad that it has to be mathematics, and that mathematics for some people is hard. When it's reputed, I don't know if it's true, that when one of the kings was trying to learn geometry from Euclid, he complained that it was difficult. And Euclid said that there's no royal road to geometry. And there's no royal road. It's not we cannot, as people who look at this thing as a physicist, cannot convert this thing to any other language. You have, if you want to discuss nature, to learn about nature and to appreciate nature, it's necessary to find out the language that she speaks in. She offers her information only in one form. We are not so unhumble as to say, demand that she change before we pay any attention. It seems to me that it's like all the intellectual arguments that you can make would not in any way, or very, very little, will communicate to deaf ears what music, the experience of music really is. And all the intellectual arguments in the world will not convince those of the other culture. The philosophers who try to teach you by telling you qualitatively about this thing. Me, who's trying to describe it to you, which is not getting across because it's impossible. We're talking to deaf ears. And it's it's perhaps that the horizons are limited, which permit such people to imagine that the center of the universe of interest is man. Thank you.
Да, приветствую, кто подошел, ну или кто еще, в общем, меня не слышал, кто начало стрима пропустил, ну и вообще, что я говорил. Jake, if you are still here, right? В общем, если кто-то здесь, то напишите, чтобы я зря не распинался лишний раз. Embrace the shadow. Yep, nice. So, yeah, the most not important and scientific ways. Да уж, ну что ж, учи английский, что я могу сказать. Но я постараюсь и на том, дважды как бы объяснить, но тем не менее, сейчас я с Джейком немного поговорю. Дело в том, что он тоже ученый, так что профессор. So yeah, very probably my favorite part, not scientific ways, but the end of the second part of the lecture, or probably it's the last one. Yeah, it's wait. I have a third part, but oh yeah, it's a conversation with just audience. But yeah, so it's a full lecture, one and second part. So yeah, the most interesting in the end. So he's telling like all the intellectual rational arguments you can make cannot communicate with, you know, deaf people. And he's given analog like with music, deaf with music. And he's dividing, he's talking about other, I guess, not even guess, about other scientists. He's talking about C.P. Snow and his book, The Two Cultures, where he's kinda telling that there are physicists, mathematicians, and just quite simple people who don't understand, who don't understand physics and mathematicians, and that you can't conversate with deaf people, you know. It's like not like elite and not, but well, I guess you know what I'm saying here, right? And interesting stuff. It was after Second World War, and interesting that no one said a word to him because it's kind of fascist views. But never mind. So yeah, of course, I think it's a right thought overall. I mean, these analogies and overall. Короче, смотри, Сандра, такая штука. Там, конечно, если, ну, уже просто научно я уже поговорил в начале немножко, хотя не то, что научно. Короче, последнюю неделю просто очень сильно в квантовую физику. Короче, вместо отдыха, вместо того, чтобы куда-то уехать, я в итоге просидел квантовой физике, посвятил чуть ли не 70, если не больше прямых часов, то есть за последние 6 дней, вот. 70 часов, короче, общую теорию всего, потому что атом мне вообще не устраивает, ну, теория относительности Эйнштейна, там куча дыр. Вот, то есть, и как раз он говорит про CP такого Сноуа, и его книга «Две культуры». И, в общем, есть физики, математики, есть те, кто как бы не понимает красоту, the beauty of universe, красоту этой вселенной. И это все равно, что говорить с глухими, которые, ну, или глухими, которые не слышат музыку. То есть, по сути, мне даже так. Yeah, also he's saying like philosophers can teach you with just not description, qualitatively about nature, right? And like I'm trying to describe it with physics and mathematics. deal with situation, good measure of humility. Yeah, and majority, huge majority, I mean, most of people don't understand it at all. They're not trained. Well, yeah, of course they're not trained, but overall they're kind of different culture peoples, you know, different culture people, and it's like to be talking with deaf people who don't appreciate music. By the way, I have read this book, I mean by C.P. Snow, and I recommend it to you as well if you didn't read it. So that's because I know about what he's talking about. Probably if I didn't read it, I couldn't understand it, this part. But yeah, this is one of my favorite part, probably not in a scientific way, but in, you know, in just worldview thing, like people are not equal. What humility, people just are not equal. And how can you talk with well, not with philosophers, but just with people who don't appreciate the beauty of nature, physical and mathematician beauty of universe and nature. That's what he's talking about. То есть вот он о чем говорит здесь. Именно разница культур, ну, в кавычках, то есть не то, что разница культур, а именно что деление. Ну, по сути, да, что люди не равны, конечно же, такие несколько фашистские, можно сказать, взгляды, хотя, смотря что считать фашизмом, у нас сейчас абсолютно неправильно понимают это слово, но, в общем-то, верно, по сути, верно, потому что люди не равны, и реально говорить с глухими и тупыми нет никакого смысла, которые не понимают физику и математику. Это все равно, что детсадовцу объяснять теорию струн, ту же самую, да, либо там, опять же, постоянной планкой и прочего, то есть теорию общей относительности, без супергравитации, без суперструн, без, ну, то есть заниматься вот примерно тем, что 70 часов занимался, только абсолютно ничего не понимая, но то есть не то чтобы утыкивать в бесконечности там, да, и кванты, квантайзинг. Well, and again, let's watch this stuff again, I mean, this kind of parody, right? Because everything is there. That's why I like it so much, because, you know, all the problems like infinities, quantizing shit, diagrams of Feynman, and so on. Everything, this is just a genius work. This guy is fantastic. You know, it's hard to impress me, but yeah, this guy impressed me with his work. Absolutely great stuff. But yeah, let me check the chat. You know, Jake, the funny part that probably no one is completely understanding what he's, you know, not even talking about theoretical physics, and it's all a theory, like, you know, this supergravity stuff, it's all not so practical, you know what I mean, right? Of course you know, you are, by the way, yeah, you're a professor, right, already? Oh no, or you're going to be a professor, but anyway, as a scientist, as a mathematician, I think you must understand me. But yeah, you know, the critical difference between me as a physicist and I have a friend who is a mathematician, and you know, the critical critical difference, there is a critical difference in thinking. Yes. And yeah, of course, as well, it's a little bit hard for me to explain on English because of the terminology. I know, of course, I know terminology on Russian, but I'm not sure I know terminologies in English. I mean, scientific, all this scientific stuff. Despite of I'm watching a huge quantity of lectures by different scientists on English and American as well, but all over the world. So yeah, fucking infinities, and it's all in our kinda, not in all in our minds, but yeah, it's a theoretical stuff. I can even say I prefer practical, but how can you fucking made practical experiments. I don't have у меня нет Android коллайдера, у меня нет под рукой андронного коллайдера, да даже если бы был, то хули толку. В общем, такие печальные, получается, дела эти бесконечные. Ну, в общем, спины, попробуй в исходное положение 720 градусов, короче, вообще. Еще бы, если бы я не сделал перерыв, я просто в дурку бы поехал с этими спинами, с этими бесконечностями. В общем, But yeah, anyway, let's not drop it. Let's try to make a theory of all, because yeah, relativity of Einstein's it's not complete at all. Okay, let's watch it one more time. I mean, this great a cappella science defining gravity. What a great work. Yeah, this epic win. I really can say it's an epic win. Let's watch it.
Hey there, musical scientists!
Oops, it's the wrong one. It's again. It's not. No. I mean, not define gravity. I mean, of course, Bohemian gravity. Yep.
Well, that took a while.
Yeah, that took a while.
Theory, right?
For
Is
sure.
it just fantasy?
Great stuff.
Caught in the landscape, out of touch with reality. Compactified on S5 or T-star S3. Space is a pure void. Why should it be stringy? Cause it's
Indeed.
quantum not classical, non-renormalizable. Any way you quantize, you encounter
Infinity, damn it.
You see. Quanta must interact via paths we understand, using Feynman diagrams. Often they will just rebound, but now and then they go another way. A quantum loop. Infinities will make you cry unless you can renormalize your model of baryons, fermions, and all other states of matter.
Yeah, with supergravity and super strings theories.
Curved space, the graviton can be thought of as a field, but these infinities are real. In a many-body loop diagram, our results diverge no matter what we do. A quantum soup. Kiss your fields goodbye. Guess Einstein's theory wasn't complete at all.
Einstein theory was not complete at all.
What's their use? What's their use? Do they give us quark plasma? Can we minimize what function or describe this state?
Nambu-goto, Nambu-goto, how to quantize, I don't know.
Nice that he's mentioned Polyakov here.
Just a world sheet from a string theory, re-parameterized by a vital symmetry.
Thermibos, open, closed, orientable.
Vibrations, balls, they become particles. Vibrations, they become particles. Vibrations, they become particles. Become particles. Become particles.
Oh, mamma mia,
Suggestive particles. A tachyon, a dilaton, and gravity.
So we need 10 dimensions, and I'll tell you why.
Or maybe even 11.
To get down to 40, we come back to 5. Caleb. Manifold must be Caleb. If we want to preserve any of our symmetry.
Super strings I took one to A and to B. Heterotic O and heterotic E. All are one through S and T-duality. Thank you, Web10 for that superstring revolution and your new M theory.
Super young man, like to be true. Duo, molecules and atoms, light and energy, time and space and matter, all from one united theory.
Yep. Anyway, you quantize. So yeah, probably all united theory. That's it. We will not surrender. We will go to the end. Then, great stuff. And Jake, yeah, I wanted to say something. Oh yeah, you was talking about definitely chasm of understanding. No. Later. Wait. Yeah, extremely frightening if you were not a scientist, it would be. And if you didn't understand nature. Well, probably, if not, then you could be kinda, an animal. I mean, not an animal, but human animal. I hope you know what I mean. Just, we have term like that in Russian, but I guess you have in English as well. I just not sure which one is it. So, and yeah, I think you wouldn't be frightened at all. You just will not give a fuck about it. You will sleep, eat, fuck, and that's it. You know what I mean. A lot of cards. Let's just disenchant it. Yeah, quantized infinities. That's why I spare a lot of time in it, but anyway, not so successfully, It's all about not all about imagination, but yeah, I don't have a collider. I don't have. It's sadness. Could be fun if it would not be so sad, actually. Ну, вообще-то. Да, математика тоже интересная, квантовая физика, безусловно. Но я все-таки на самом деле предпочитаю практическую, но квантовая теоретическое тоже. Но я говорю, с ранней юности просто меня не устраивала теория Эйнштейна, поэтому я делал попытки докопаться до истины, но это не совсем, ну, не так просто, это было бы огромным преуменьшением. Вот. Бывает иногда, то есть что-то втемяшится и начинаю буквально там вообще без сна практически что-то вытворять, исследовать. Так что да. Ну, радует, что у меня в подписчиках 5 профессоров, как минимум, конечно. Помимо меня, хотя я не особо себя за профессора считаю, но это все бумажки полные лажа и говно. В принципе, главное это интеллект и понимание и осознание. Так что насчет невообразимо тут ты не прав. Можно это, в принципе, вообразить. И даже 10 дайменшенов, и даже 11. То есть параллельных, как бы, ну, это сложно, конечно, да, но, в принципе, возможно, как и все эти спины и возврат в то же положение, там, через... В принципе, можно. Просто надо, как бы, расширять знания. Так, музычку поставить, чтобы не фонил микрофон. Кстати, как сегодня фонит, не фонит? Вот этот в смысле? Да я вообще предпочитаю квадраты. То есть я не люблю окружности, конечно же. Как и все рациональные люди, я предпочитаю твердые формы, а не округлые. Я же не говногуманитарий, который кружочки будет любить. Разумеется, нет. So yeah, I think there is no reason to, continue the discussion. Not a continued discussion, watching discussion of Feynman and audience. So I guess soon it will be the end of the stream. And yeah, time for me as well. Because maybe tomorrow I will finally go to the nature, forest, mountains, so on, you know. Да, так что я уже даже не завтра, а сегодня, вероятно, уеду. Ну, вероятность как бы еще не 100% и даже не 90%, но 70, я думаю, 70-80% есть, потому что штормовая погодка кончилась, и хочется выехать, отдохнуть, отвлечься, а то можно так поехать. Хотя, чё, я и так уж поехавший давно как. Но, да, нужно отвлечься, короче, в лес, в горы, ну, хотя бы если недалеко, то, да, съездить отдохнуть. Вылазки иногда делаю, так что иначе по-другому просто как-то не могу, иначе совсем тяжко. Что от всего отвлечься. Ну и да, там уже все, можно сказать, отпуск такой, и, в общем, отдых кончится, но тем не менее, да, пока стримить завязывать не планирую, так что. Но я думаю, даже ненадолго, на неделю даже нет, на пару дней хотя бы. Вот. Но да, с такими вечными дождями, сейчас с штормовыми погодами, может еще и посмотрим. Завтра по обстоятельствам посмотрю. Вот. Прогнозы как бы меня не очень интересуют. У меня как бы помимо знаний по погоде, ну то есть еще интуиция, как у пауков. Если кто не знает, пауки там начинают плести усиленно, ну или наоборот, расплетывать свои паутины. Так что, ну что-то вроде того, короче. Я знаю, что сейчас дожди будут по-любому. Ну вот несколько дней вроде более-менее. Хотя ладно, не будем уже в такую... Кстати, да, было, я так как раз рассказывал недавно человеку, как голландцы, можно сказать, не то что победили в войне, но бой там, учитель Наполеона лично там вел, в общем, командование, и такая штука была, в общем, ну, дожди шли, все дела, и прислали послание, а там говорилось, что пауки начали, в общем, плести усиленно паутину. Но это значит, что такая холодная, сухая погода. Ну и действительно, там река замерзла, они перешли, в общем, и выиграли там ключевое сражение. Ну это так. Это вообще к науке сейчас никакого отношения не имеет. Я просто ради интереса рассказываю, может, кому будет интересно. Что да, погода не радует. Хотя, ну как не радует? Это мне лучше, чем жара плюс 30. Я жару вообще не люблю. Лучше, конечно, грозы, громы и все такое, и дожди, но если вот ехать куда-то, то это не очень. Это не очень. Не то, что там рыбалка, охота, но и это в том числе. Просто на природу, в лес, горы, то... В общем, когда дожди, это совсем нехорошо. Нехорошо. Как раз нужна сухая погода для поездок. Ну, желательно. Да не, какое все лето. Так, хотелось бы, конечно, подальше куда-нибудь на север вообще там, но далеко, наверное, уже не поеду. Так, возможно, Карелия какая-нибудь. Ну, уже думал-то, хотели или на Волгу, либо еще куда, но в итоге ни хера. Ладно. Посмотрим. Да, вообще посмотрим, куда глаза глядят. С товарищами съездим завтра. Ну, завтра, либо не завтра, а через пару дней. Но съездить все-таки хочется. Хотя бы на дня 3 вырваться. Палатку брать, не брать. А, можно и в машине, в принципе, поспать. Но это не очень удобно. Ну ладно, не будем уже об этом. Честно говоря, не очень хочется об этом на стриме публично рассказывать. Но суть в том, что да, если не будет стримов, значит я уехал. Либо опять во что-нибудь углубился в какую-нибудь физику квантовую. Но не, я думаю, надо перерыв сделать. Но некие успехи есть. Ну, то есть не то, что, конечно, прям общую теорию всего, но... Дело в том, что немножко подзабыл, заодно напряг извилины память и стал еще глубже все дело понимать и осознавать. Так, сейчас еще чатик я что-то явно, наверное, пропустил. В своих рассуждениях опять же углубился. Так. Yeah, practical purposes, Jake. Of course. That's what I was talking about. Yeah, I think there are a huge quantity of people who not even try and just understand in nature in a totally wrong way and key. With philosophy, religions and fucking bullshit. Just to say in it cynical way. Of course I'm damn right. How can I be wrong about that? I mean, they're not even understanding problems. They're not even trying. They're not even trying. And that is the problem. And the sad part that they're okay. They're kinda okay with it. They're totally fine. Very sad. But it's just like as it is, you know. It's like sad. I guess I can say like sad axiom, which we just must take, or we need to take again about the two cultures and about in the end what was Feynman was talking about, kind of same key. He just couldn't, of course he couldn't talk to audience like I'm talking cynical, but yeah, it's by the way it's actually cynical in different ways, but as I already said, it's kinda right in the face, punching on the face. He was punching audience in the face, I can say symbolically. Oops, music was too loud probably, or not, I'm not sure. I hope not. But yeah, it's an ambient. So yeah guys, I think that's it. soon I will just go to sleep, and I shall see if I will go ride or not because of weather. Or maybe I will stream. If not, I will probably stream in the evening. Or maybe not even in the evening. So anyway, thank you for watching. It was a great stream. Of course, not totally not for all, but yeah, Jake, especially yeah, to you, Jake. It was a pleasure to discuss this stuff with you. Well, and with others as well. С другими тоже. Спасибо, кто смотрел. На СК там даже люди были, вроде кто-то интересовался, но, как всегда, легкие рели. Totally welcome. Totally welcome. So yeah, it was a great stream. I really enjoyed it, and this lectures, discussion. Stay tuned, mates. See you next time.